The furthest object in a photograph and the closest object in a photograph are usually easy to tell apart, usually. A little over a year ago, the James Webb Space Telescope photographed a famous patch of sky and found two faint red dots that looked, by every test we had, like galaxies from the very dawn of time, more distant than anything ever recorded. But one team had a quiet doubt, so instead of announcing anything, they waited a full year, aimed the telescope at the exact same spot, and took the photo again. And this time, the two dots had moved, which should be impossible, unless the most distant thing in the picture was also, somehow, one of the closest. To understand why two small points of light cause so much quiet excitement, we need to start on a particular night, and in a particular place in the sky. The James Webb Space Telescope does not orbit the Earth the way the older Hubble telescope does. It sits about 1.5 million kilometers away from us, roughly 930,000 miles, at a calm gravitational parking spot known as L2. Out there, shielded from the sun by a tennis court-sized sun shield, its mirror stays cold enough to see the faint warmth of the early universe. And on this particular night, that mirror was pointed at a small, unremarkable-looking patch of sky in the southern constellation of Carina. Unremarkable is the wrong word, though, because this patch of sky is one of the most famous addresses in modern astronomy. It contains an object called the bullet cluster, and the bullet cluster has a story of its own worth pausing on, because it is part of why the telescope was looking here at all. At first glance, none of this seems to have anything to do with two tiny red dots. But without understanding why Webb was looking here in the first place, it is impossible to understand why those dots looked so extraordinary. The bullet cluster is what you get when two enormous clusters of galaxies crash straight through one another. That collision happened around 3.8 billion years ago, and we are seeing it from a distance of roughly 3.7 billion light-years. When astronomers led by Douglas Clow studied it back in 2006, they noticed something that has stayed famous ever since. As the two clusters passed through each other, the hot gas between the galaxies got dragged and slowed down, a bit like two runners wading through a swimming pool, while everything they are carrying gets held back by the water. But the mass of the clusters, measured by the way it bends the light of more distant galaxies behind it, sailed straight on ahead, completely separate from the gas. The only sensible way to explain that gap is that most of the mass is made of something invisible that barely interacts with anything, something we call dark matter. That result is still regarded as one of the most direct pieces of evidence we have that dark matter is real, and this year marks 20 years since it was published. There is a second reason astronomers love pointing telescopes at the bullet cluster, and it matters a great deal for our story. All that mass does something useful to the light passing near it. It bends that light, and in bending it, it magnifies whatever sits far behind the cluster, stretching and brightening distant galaxies that would otherwise be far too faint to detect. In other words, the cluster works as a giant natural lens, doing some of the telescope's job for free. So if you want to catch the faintest, earliest galaxies in the universe, the ones that formed in the first few 100 million years after the Big Bang, the bullet cluster is a very sensible place to aim. It is worth pausing on just how powerful that natural lens is, because it is the reason such a small telescope, in cosmic terms, can reach so far. Light does not travel in a perfectly straight line when it passes a great concentration of mass. The mass warps the space around it, and the light follows that warp, bending as it goes by. A cluster as heavy as the bullet cluster bends the light of everything behind it, quite dramatically, gathering rays that would otherwise have spread out and missed us entirely, and focusing them towards our telescopes. It smears distant galaxies into thin, glowing arcs, and it brightens them, sometimes by a factor of 10 or more. Nature, in effect, has built us a telescope far larger than anything we could ever launch, and left it hanging in the sky for free. Point Webb through the middle of it, and you can see fainter, and therefore further, than the telescope could ever manage on its own. And without that cosmic magnifying glass, our story would probably have ended before it even began. Those two mysterious dots would have been far too faint for anyone to notice. That is exactly what this program set out to do. Webb stared into the field for hours, gathering light through a series of filters, each one tuned to a slightly different slice of the infrared, building up an image far deeper than any taken of this region before. When the pictures came back and the team began sifting through them, most of what they saw was reassuringly ordinary. There were background galaxies of every shape and color, foreground stars from our own Milky Way that showed up cleanly in every filter, and the usual specks, hot pixels and blemishes that come with any deep exposure. And then, tucked into one corner of the field, there were two small, faint red points of light that did not behave like anything else around them. The two dots sat very close together, separated by an angle so small it is hard to picture. Astronomers measured it at just under 13 arcseconds. If that means nothing to you, here is a way to feel it. Hold a single human hair up at arm's length. The thickness of that hair, from where you are standing, is about the same tiny angle that separated these two dots. They were practically neighbors in the sky. What really caught the team's attention was how the dots appeared, or rather how they disappeared. In the bluer filters, the ones that catch shorter wavelengths of light, there was simply nothing there. Move to slightly longer wavelengths, and still nothing. Keep going, further and further into the infrared, and only in the very reddest filters did these 2 points finally switch on and start to glow. Astronomers have a name for objects that behave like this. They call them dropouts, because the object drops out of the shorter wavelength images entirely and only shows up in the long ones. And a dropout is a very particular kind of clue. For 30 years, that sudden switch from invisible to visible, always at the same point in the spectrum, has been one of the most reliable fingerprints we have for a galaxy sitting at the very edge of the observable universe. By every rule the team had, these two faint red points looked like the most distant objects ever seen, their light stretched and reddened by the entire history of the cosmos. You can imagine the quiet excitement in the room. Everything about these two dots fit. They were exactly where the deepest, most magnified part of the field was. They were faint, which is just what you would expect from the most distant galaxies of all. Their colors matched starlight that had been stretched so far by the expanding universe that it had slipped entirely out of the visible and into the deep infrared. If you had asked any astronomer to sketch what a record-breaking early galaxy should look like in this data, they would have drawn something very close to these 2 points. And if the team had trusted that fit, the numbers were extraordinary. Taken at face value, one of the dots would sit at a redshift of around 30, the other at around 20, which would place them among the very first structures ever to form in the universe. It was the sort of result that ends up in textbooks, which is precisely why nobody wanted to be wrong about it. So by every test we had, these were the oldest things ever recorded. And that rule was about to meet the one exception nobody had planned for. Because before the team let themselves believe what they were looking at, they wanted to understand the trick of light that made this fingerprint so trustworthy in the first place, and they knew that same trick had a weakness hiding inside it. So why does a dropout tell you that something is unimaginably distant? The answer is one of my favorite pieces of astronomy, because it comes down to the most common substance in the universe doing something very simple over and over again across billions of light years. That substance is hydrogen. The early universe was made almost entirely of it, and even now, more than 13 billion years later, hydrogen is still by far the most common thing out there. It is scattered thinly through all the empty space between the galaxies, and it has one very particular habit. It is hungry for light of a certain color. Any light with a wavelength shorter than a specific threshold gets absorbed by hydrogen atoms along the way, soaked up before it can reach us. Light with a slightly longer wavelength passes straight through, untouched. The threshold sits at a wavelength of about 912 angstroms, deep in the ultraviolet, which is just a fancy way of saying it takes exactly this much energy to knock the single electron off a hydrogen atom. Above that energy, the light gets eaten. Below it, the light survives. So when you look at a distant galaxy, its spectrum, the spread of all its colors laid out in order, has a sharp step in it. On one side, the light is more or less intact. On the other side, it has been almost entirely stripped away. Picture a cliff edge in the brightness. That cliff is the fingerprint we are hunting for. Now here is where the expanding universe comes in, and this is the part that makes the whole method work. As the universe expands, it stretches the light traveling through it. The further away a galaxy is, the longer its light has been on the road, and the more that light has been stretched by the time it reaches us. Stretching light means shifting it towards the red, longer wavelength end of the spectrum, which is why astronomers call this redshift. And crucially, the cliff gets stretched along with everything else. If the idea of light being stretched feels slippery, here is a familiar version of it. Think of an ambulance racing past you with its siren blaring. As it comes towards you, the sound is high and sharp, and the moment it passes and speeds away, the pitch drops to a lower, deeper note. The sound waves are being stretched out as the ambulance recedes. Light does something very similar. As the universe expands and carries distant galaxies away from us, their light gets stretched to longer, redder wavelengths, and the further the galaxy, the greater the stretch. The hydrogen cliff rides along with it, sliding steadily towards the red. For a nearby galaxy, that cliff sits in the ultraviolet, where most telescopes on the ground struggle to see it anyway. But push a galaxy far enough away, and the cliff gets dragged out of the ultraviolet, through the visible colors, and eventually all the way into the infrared. So if you take pictures of the same patch of sky through several filters, and you find an object that is completely missing in the shorter wavelength filters, but suddenly appears in the longer ones, you have almost certainly found a galaxy whose cliff has been stretched to sit right between those two filters. Measure where the cliff lands, and you have measured how far away and how far back in time you are looking. This idea has a birthday. In 1996, An astronomer named Charles Steidl and his colleagues used it to hunt down galaxies whose light had left them when the universe was a fraction of its current age. The very first galaxies they caught this way vanished in the ultraviolet filter, so the objects earned the nickname U-band dropouts. The technique caught on quickly because it had a wonderful reputation. It was clean, it barely ever confused a nearby object for a distant one, and for decades it was celebrated as a method almost free of false alarms. And it delivered, again and again. The Hubble Deep Field in the 1990s was full of dropouts. The method helped identify, and its even deeper successor, the Hubble Ultra Deep Field, pushed the same trick further still, pulling faint early galaxies out of what looked, to the eye, like an empty patch of black sky. Later surveys extended the catalog into the hundreds and then the thousands of early galaxies. By the time the James Webb Space Telescope started work, this humble trick had been checked and rechecked on more distant galaxies than anyone could count, and it had a remarkable habit of being right. When you found a dropout, you had found a galaxy. That was the rule, and it had earned its trust across 30 years. James Webb then took the method somewhere it had never been. Because Webb sees almost entirely in the infrared, it can catch the hydrogen cliff for galaxies so far away that their light left them within the first few 100 million years after the Big Bang. The longest filter on its main camera is the last stop on this journey, the filter where a dropout could mean a galaxy right at the frontier of everything we can observe. When the Bullet Cluster team saw two faint points appearing only in those very longest filters, with a clean, sharp cliff exactly where it should be, they were looking at precisely the kind of object this technique was built to find. So a dropout almost always means a distant galaxy. Almost. And it turns out the whole story lives inside that one small word. Because there is something else in the universe, something far closer and far stranger, that produces almost exactly the same cliff, in almost exactly the same place, for reasons that have nothing to do with distant galaxies at all. The team knew about this weakness. They had watched it catch other astronomers out, and it was the reason they refused to celebrate just yet. Before we get to that weakness, it helps to sit for a moment with what these two dots would mean if they truly were galaxies, because the stakes are hard to overstate. To feel it, you need a rough sense of the calendar of the universe. The cosmos is about 13.8 billion years old. For the first few 100,000 years, it was too hot and dense for light to travel freely at all. Then it cooled, went dark, and slowly the very first stars began to switch on somewhere between 100 and 200 million years in. The first proper galaxies, great collections of those early stars, are thought to have assembled a few 100 million years after that. Now hold the two dots up against that calendar. If they really were galaxies, the fainter one would be sitting at a redshift of around 20, meaning we would be seeing it as it was when the universe was only about 180 million years old. The other would be even more extreme, at a redshift of around 30, when the cosmos had existed for barely 100 million years. That is right in the window when the very first stars were only just flickering into life. There should not yet be a fully formed galaxy there at all, bright enough for us to see, even with a natural lens helping us out. To give you a yardstick, the most distant galaxies we have, actually confirmed, sit at a redshift of around 14, Take one of the current record holders, a galaxy called James Z14, first announced in 2024. We see it as it was when the universe was roughly 290 million years old, only about 2% of its present age, and it already contains hundreds of millions of times the mass of our Sun in stars. That galaxy alone is surprising enough that it has kept theorists busy. Our two red dots, if genuine, would be sitting 100 million years earlier still, in territory where our best models of how galaxies form simply do not have a comfortable answer. It is worth spelling out why that is such a problem, because it is not just a matter of setting a new record. Building a galaxy takes time. You need gas to cool and collapse, stars to form, and enough of those stars to gather together to make something bright enough for us to spot from across the entire universe. Our best models of how all this unfolds, built up over decades, and tested against everything we had seen before, suggest that in the first 100 million years, there simply was not enough time to assemble a galaxy that luminous, even if star formation ran flat out. So an object like this would not just be far away. It would be telling us that galaxies grew faster, or brighter, or in some way differently from everything we thought we understood. Ever since James Webb switched on, there has been a steady drumbeat of headlines claiming it had broken our model of the early universe, and a genuine, confirmed galaxy at a redshift of 30 would have been the loudest of them all. I should add one honest note here, because the record does not stand still. As of early 2026, that title of most distant confirmed galaxy has quietly changed hands. A newer galaxy called MOM Z14, at a redshift of around 14.4, has edged ahead of Jade's GZ14, which was itself revised slightly. So when I say these dots would smash the record, I mean they would leave both of those confirmed galaxies far behind, by more than 100 million years of cosmic history. If the team could prove that, it would not be a small result. Every theory of how the first galaxies grew would need rewriting, and headlines about James Webb breaking cosmology would write themselves, which is exactly why the team felt so cautious, and this is where a ghost enters the story. Because they had seen a case very much like this one before, and it had not ended cleanly. A couple of years earlier, in a different deep field, astronomers had found another single faint red dot with an even more extreme dropout, one that suggested a redshift of around 32 if you took it at face value. The object picked up a nickname, Capitaro, and it became a puzzle the community kept circling back to. Capitaro would not settle down. When teams studied it carefully, they found not one, but 3 possible explanations, and every one of them was remarkable in its own way. The first was that it was exactly what it appeared to be, a galaxy at a redshift of around 32, seen when the universe was barely 90 million years old, which would make it the most distant object ever found and would force us to rethink how quickly galaxies can possibly grow. The second was that it was a cold, failed star in our own galaxy, close by, and quietly wearing the disguise we have been describing. And the third was the most exotic of all, that it might be the final explosion of one of the very first giant stars ever born, a titanic blast that tears the entire star apart and leaves nothing behind, its light stretched and dimmed by distance until it happens to mimic the same telltale cliff. Those 3 answers could hardly be more different from one another, One would rewrite the story of the early universe, one would add to a hidden population in our own backyard, and one would be the first direct sighting of a kind of stellar death that has only ever existed in theory. Later analysis leaned towards the closer, colder option, the failed star, but the data would not fully commit, and the case is still not closed today. Some studies even hinted that the object was flickering slightly in brightness, in a way a simple failed star should not, which only deepened the puzzle rather than solving it. So the Bullet Cluster team knew the trap. They had a phrase they kept repeating to each other, half joking and half serious. The most distant thing in the picture, they said, might also be the closest. Until they could prove otherwise, these two beautiful dropouts could go either way. And they knew that in astronomy, when something looks too good to be true, it very often is. So instead of writing the paper of the decade, they decided to do the one thing modern science almost never has the patience for. They waited. It sounds like such a small thing to do, but in a field where careers are built on being first, and where a result this big would have made headlines around the world, choosing to sit on it for a year takes a real kind of nerve. They could have published. They had a clean dropout in a lensed field in the most famous dark matter image in the sky. Any journal would have taken it. Instead, they went looking for ways to prove themselves wrong. That instinct is one of the quiet virtues of good science, and it is worth admiring for a moment. The history of astronomy is littered with beautiful results that turned out to have ordinary explanations, spotted only because someone was patient enough to keep testing after the exciting answer had already arrived. The team had a fresh example sitting right in front of them, in the shape of Capotaro, still unresolved, still refusing to give up its secret. They had watched that puzzle stretch on for years, so they knew, better than most, that the honest move was not to announce and defend, but to wait and check. They even prepared for both outcomes, drafting the story two different ways, one in which the dots were galaxies at the dawn of time, and one in which they were something far closer, so that whichever answer the universe handed back, they would be ready to tell it straight. Their first move was to ask for time on Webb's spectrograph, an instrument that spreads an object's light out into a full rainbow, rather than just catching it through a handful of filters. If the dots were galaxies, that rainbow would tell them so. If the dots were something colder and closer, the rainbow would carry a different signature, the marks of molecules in a cool atmosphere. Early in 2025, that spectrum came back, and it was, frustratingly, not quite enough. The shape of the light leaned gently towards the closer, colder explanation, a failed star rather than a galaxy, but it leaned only gently. On the numbers alone, the team still could not rule out a galaxy with confidence. They needed a cleaner, harder test, one that did not depend on interpreting the fine details of a faint rainbow at all. And there was such a test, sitting in plain sight. It is one of the oldest tricks in astronomy, and it comes down to a single question: does the object move? Think about what it means for something to be at the edge of the observable universe. Its light has been traveling towards us for almost the entire history of the cosmos. Even if that galaxy were racing across space at an incredible speed, it is so unimaginably far away that, from our point of view, it would appear frozen in place. Watch it for a year, for a decade, for a lifetime, and it would not shift by any amount we could ever hope to measure. A true distant galaxy has, for all practical purposes, zero sideways motion across the sky. A cold object inside our own galaxy is a completely different matter. If one of these dots were a nearby failed star, drifting through the outskirts of the Milky Way, then over the course of a year, it would slide a tiny but genuinely measurable distance across the sky. Astronomers call this sideways drift proper motion, and it is the sort of thing that separates a lamp on the far side of a city, which seems fixed, from a firefly a few meters away, which visibly moves as you watch. So the plan became beautifully simple. Point Webb at the same patch of sky 1 year later, take the same picture, lay the two images on top of each other, and see whether the dots had budged. This is not guesswork, by the way, and it is worth saying so plainly, because it is easy to imagine astronomers simply squinting at fuzzy blobs and arguing. The method is precise. You line the two images up using the background stars and galaxies that you know are not moving, and then you mark the position of your target in each image with a small circle. If the circles land on top of each other, the object is fixed, and the galaxy explanation survives. If the circles are offset, and offset in a sensible direction, the object is a local one, and it has quietly given itself away. The same technique had already been used to catch other suspects. In earlier surveys, objects first catalogued as candidate distant galaxies had been re-examined this way and revealed as nearby failed stars, drifting exactly as a local object should. So the team were not inventing a test. They were applying a standard, trusted check to the most tempting targets they had ever found. They scheduled the second picture for 1 year and 1 day after the first, to give themselves the cleanest possible baseline to measure against. And then there was nothing left to do but wait for the calendar to turn. If the dots had not moved, this would be the discovery of the century. If they had, it would be something far closer to home and far stranger than a distant galaxy. A year later, almost to the day, Webb swung back to that same patch of sky, took the shot, and sent the data home. Picture the moment, late in the day, somewhere in an ordinary office, a member of the team opens two images on a screen, side by side. One was taken a year ago, the other arrived only a few days back. Both have already been carefully lined up against the fixed background of stars and distant galaxies, the ones we know are not going anywhere, so that if anything in the frame has genuinely moved, it will stand out. And there, in both pictures, sit the two faint red dots that have kept this team patient through 12 long months. They move the cursor to the first dot in the older image, then to the same dot in the newer one. And the position has changed. Not by much. It is the kind of shift you would never catch with your own eyes, the kind that takes the sharpest infrared telescope ever built to register at all. But it is there. Over a single year, that dot has slid a small, definite step across the sky. To get a feel for how tiny that step is, imagine trying to watch a single strand of hair move sideways from several kilometers away. Almost nothing. And yet, for a galaxy at the edge of the universe, almost nothing is already far too much. That number was supposed to be a flat, perfect zero, because an object that far away, with its light traveling toward us for nearly the whole history of the cosmos, cannot appear to move in a single human year, no matter how fast it is really going. This dot had moved, and that one fact was enough to settle the whole question. They checked the second dot. It has shifted too, a little less than the first, but with no room for doubt. and both dots have drifted in the same direction, holding their spacing almost exactly. Whatever these two objects are, they are traveling through space together, side by side, like two boats carried along on the same current. That detail, that they move as a pair, is a clue all on its own. It might mean they are genuinely bound to one another, two objects held together by gravity and drifting through the galaxy as partners, the way so many stars come in twos. Or it might be a trick of perspective, two unrelated objects that happen to lie at a similar distance and happen to be heading the same way, lined up by chance along our line of sight. The team cannot say for certain yet, and honestly, either answer is its own small marvel. What they can measure is the speed. From that tiny yearly shift, the brighter of the two works out to be moving at around 116 kilometers per second, which is roughly 72 miles per second. The answer is a strange little coincidence buried in the laws of physics, and once you see it, the whole story clicks into place. Cast your mind back to that cliff in the spectrum, the sudden step from bright to dark that marks a distant galaxy. For a galaxy, we know what makes it. Hydrogen in the vast space between the stars soaks up all the light shorter than a certain wavelength, leaving a clean edge. Now consider the second object in our story, a cold, failed star. It has an atmosphere, and that atmosphere is full of molecules, chief among them methane and water vapor. Those molecules are also fussy about which colors of light they will let through. They absorb strongly across certain bands of the near-infrared, dimming the object dramatically at shorter wavelengths, while letting it shine through more brightly at longer ones. And here is the coincidence. The step this creates in a cold star's light happens to fall in almost exactly the same part of the spectrum and to have almost exactly the same shape as the hydrogen cliff of a galaxy at the dawn of time. Two completely unrelated processes, one playing out across 13 billion light-years of empty space, the other happening in the swirling clouds of a single failed star just down the road, end up leaving the same mark in our data. When astronomers first started calling this what it is, they described it beautifully. They said the universe had handed us two different words that happened to be spelled the same way. Read at low resolution, through a handful of broad filters, you genuinely cannot tell them apart. I want to be careful here, because it would be easy to say the method failed. It did not fail. The dropout technique worked exactly as designed. The trouble is simply that nature built two entirely different objects that leave an identical signature, and no clever tweak to the method can undo that, because the coincidence lives in the physics itself, not in the technique, which is why the team needed that second, independent test. The rainbow spectrum hinted at the answer. The sideways drift confirmed it beyond argument. Put together, there was now only one thing these two dots could be: cold, failed stars of the coldest kind we know. So what actually is one of these things? The proper name is a brown dwarf, and the friendliest way to think of it is as a star that never quite made it. Stars form when a great cloud of gas collapses under its own gravity, heating up at the center until it becomes hot and dense enough to ignite nuclear fusion, the engine that makes a star shine steadily for billions of years. A brown dwarf forms the same way, from the same kind of collapsing cloud, but it comes up short on mass. The center never gets quite hot enough to light that engine. So instead of switching on, the object simply glows with the leftover heat of its own formation, and then spends the rest of eternity slowly cooling down, fading gently into the dark. Astronomers sort these cooling objects into a sequence by temperature, using a run of letters that goes M, L, T, then Y. The warmer ones near the top still glow a dull red. As you move down the list, they get cooler and dimmer, and their atmospheres fill up with more and more of the kinds of molecules you would find in the clouds of a giant planet. By the time you reach the T class, the atmosphere is thick with methane, much like Jupiter's. And at the very bottom of the sequence sit the Y class, the coldest failed stars we know of, so cool that they are barely giving off any visible light at all. They are the faded embers at the end of the line, and they are exactly what these two dots turned out to be. And this is where I have to tell you the detail that stopped me in my tracks. When the team measured the temperatures of these two objects, they came out at around 350 Kelvin for one and 410 Kelvin for the other. Let me translate that out of scientist. 350 Kelvin is about 77 degrees Celsius, or 171 Fahrenheit. That is roughly the temperature of a cup of tea that has been sitting out on the counter for a few minutes, cooling down, still warm, but no longer scalding. The other one is a bit hotter, closer to a slow oven. These were the objects that the most powerful telescope humanity has ever built had spent a year mistaking for galaxies at the beginning of time. The most distant thing in the picture had the temperature of a forgotten cup of tea. And these two are not some freakish one-off. The very coldest failed star we currently know sits just 7.5 light years away, practically next door in cosmic terms, closer than most of the stars you can name. It goes by the catalog name WISE 0855, and its temperature has been measured at around 275 Kelvin, only a couple of degrees Celsius, colder than a winter's day on Earth, with what look like clouds of water and ice drifting through its atmosphere. It weighs only a few times as much as Jupiter, so a cold, dim, genuinely peculiar object like this is not exotic at all. There is one sitting in our own neighborhood. If you could somehow stand on one of the bullet cluster brown dwarfs, though you never could, it would be an eerie place. There would be no sun in the sky, because it orbits nothing and has no star to warm it. The air around you would be thick, warm, and humid, heavy with methane and water, and a faint chemical tang, glowing dimly in the infrared from the object's own fading heat. Above you, only darkness. And it would have been like this for a very long time. Working backwards from how cold it has become, this object has been quietly cooling for something like 10 billion years, which makes it older than the sun, older than the Earth, older than almost anything you have ever thought of as ancient. It was already drifting through the young Milky Way, alone in the dark, long before our own solar system existed. If two of these could hide inside a single, carefully studied image, the obvious question becomes, how many more of them are out there? So how many of these hidden objects are there? As it turns out, a great many. And that is the part that reframes the whole story. While the Bullet Cluster team were chasing their two dots, other astronomers had been steadily turning up the same kind of object all across the deep sky. One major survey, led by a team including Kevin Hainline, went hunting through Webb's deepest images and pulled out dozens of these cold, failed stars, sitting in the very same fields where we go looking for the first galaxies. And when you take those numbers and scale them up to the whole galaxy, the totals are genuinely startling. A careful estimate a few years ago put the number of brown dwarfs in the Milky Way somewhere between 25 and 100 billion, set against the 100 to 400 billion ordinary stars. Sit with that ratio for a moment. It suggests there could be roughly one failed star for every two real ones. So when astronomers say the Milky Way is, in part, a galaxy of failed stars, they are not reaching for a poetic line. They are describing a real and enormous population, one that older telescopes were simply never sensitive enough to notice. Our galaxy has been carrying these dim, cooling embers all along, and we are only now building instruments sharp enough to pick them out of the dark. It quietly changes the picture of our own galaxy too. We tend to imagine the Milky Way as a sparkling sea of stars with a great deal of empty black in between. But threaded all through that emptiness is this second hidden population, cooling slowly over billions of years, most of it far too faint for even Webb to catch. For every one of these failed stars we manage to spot, there are many more drifting past unseen. The galaxy is a good deal more crowded with dim, patient things than any star map would ever let on. That reframes what happened with the two dots. They were not a freak accident, and they were not a failure of anyone's judgment. They were an early, spectacular example of a population we are only now able to see at all, and the way the community handled it is worth admiring. Rather than burying the awkward result, astronomers published it in the open, worked out how often this kind of mix-up actually happens, and set about tidying the catalogs. It is worth answering a fair question head-on, because you might well be thinking it. Could this whole thing simply be a mistake? Some quirk of the lens or the instrument fooling everyone? The honest answer is no, and for a solid reason. A real sideways drift, measured against a whole field of fixed background stars, moving in a consistent direction over a full year, is not the sort of thing a lensing quirk or a calibration slip can invent. The background stars anchor the frame, and the dots moved against them. In astronomy, evidence rarely comes cleaner than that, and this was never going to be a one-off tidy-up. The same careful check is now being turned on other suspicious cases scattered across the deepest surveys, with fresh images scheduled to catch any of them in the act of drifting. For certain kinds of faint object, the fraction of imposters is far from small, which is exactly why every extreme candidate is now treated as a suspect until it has passed the same simple test. Does it move across the sky, or does it hold still? There is a bigger idea hiding in all of this, and it is the part I keep turning over in my head. Most of us carry a tidy mental map of the universe. Here is our own galaxy, full of familiar stars. Out there, far across the emptiness, are the other galaxies, and at the very furthest reach, right at the edge of what we can see, sit the first galaxies of all, glowing faintly at the beginning of time. Near is near, far is far, and the two never touch. What the bullet cluster story shows is that this map has a soft, blurred region right at its distant edge. There is a thin fog of cold, local objects that can imitate the most far-flung things in the sky so convincingly that even our best instruments are briefly taken in. The oddness we thought belonged to the dawn of time had, in this case, simply moved. It was in our own neighborhood the whole while. And there is a real relief buried in that, one that settles some of the drama of recent years. When Webb first started sending back images that seemed to show impossibly early, impossibly bright galaxies, plenty of people wondered aloud whether our whole model of the cosmos was in trouble. Some of those early candidates are real, and they are genuinely teaching us new things about how quickly the first galaxies grew. But some of the most extreme ones, the very furthest of the far, are now turning out to be these cold local imposters instead. Clear the imposters out, and the tension eases. The universe looks a little less broken than the loudest headlines claimed, and a little stranger in a gentler way. Because it turns out our own galaxy has been holding a vast population of cooling embers in plain sight. There is something humbling in that, and something oddly comforting as well. The lesson is not that our methods failed us, or that the universe set out to fool anyone. It is simply that nature, every now and then, writes two very different things in what looks like the same handwriting, and the only way to tell them apart is to do the patient, unglamorous work of looking twice. And that fog cuts both ways, which is why Capitaro, the earlier puzzle that taught this team to be so careful, still sits unresolved at the back of everyone's mind. It is waiting for the very same test. A second image, a year apart, to see whether it too slides quietly sideways, or whether it holds perfectly still and turns out, after all, to be something from the true beginning of the universe. That measurement is coming, and until it arrives, the most distant thing in that picture might also, once again, be one of the closest. So the next time you come across a picture of the early universe with a bright dot labeled the most distant object ever found, you might remember these two faint red points that looked, by every honest test, like galaxies at the dawn of time, and turned out to be a pair of cold, failed stars, drifting quietly through our own galaxy, warm as a cooling cup of tea, older than the sun, and closer to us than almost any star we have a name for. They were there all along. They will still be there, cooling slowly in the dark, long after we are gone. That is the part I keep coming back to. Not that anything was lost, because the real distant galaxies are still out there, still being found and confirmed. What changed is smaller and stranger and, I think, more beautiful. The boundary between our little corner of the galaxy and the far edge of everything is not a hard wall after all. It is a soft, blurred fog of quiet objects, hiding in plain sight, patient enough to fool the finest instruments we can build. And the only way through that fog is the slow, careful, unglamorous work of measuring twice and refusing to fool yourself, which is exactly what this team did. If you would like to go one level deeper on how gravity itself can bend and magnify the light of distant galaxies, the trick that made this whole search possible, I have a video on exactly that, and I think you will enjoy it. Until then, keep looking up. The galaxy is far more crowded with quiet things than the maps let on.